All right, we're moving on to 8.7. My son is at my parents' house right now, so I'm hoping to get a bunch of these done before next week. I did not look this over ahead of time. I'm hoping that this goes well, so I apologize if it doesn't, and luckily you're the most forgiving class ever. So 8.7 is indeterminate forms and L'Hopital's rule. That's how you pronounce it, L'Hopital's. Technically there is, I believe, one of those little hats on the O, but I could be wrong. It's somewhere in there. Recall that the forms 0 over 0 and infinity over infinity are indeterminate because they do not guarantee that a limit exists. Meaning, if you get a limit and you evaluate that limit, and I apologize, I use the word limit, but we are doing limits. If you plug in the values for the limit and you get 0 over 0, we have used alternative methods to figure that out, whether it be factoring, rationalizing. This is going way back to chapter 1, or the first assessment, chapter 1. And you wouldn't be able to figure it out as is, okay? It would be a whole or something, and we'd have to figure it out using some other method. Infinity over infinity is another example, but those aren't the only examples, and we'll see some other ones that come up shortly. Nor do they indicate what the limit is if one does exist. When you encountered one of these indeterminate forms earlier in the text, you attempted to rewrite the expression by using various algebraic techniques. So we would factor, rationalize, find a common denominator, and do some sort of algebra to figure it out more simply, to eliminate some of the problems that might have been there. Occasionally, you can extend these algebraic techniques to find limits of transcendental functions. So, if I plug in 0 to this numerator, or to this exponent, I get e to the 2 times 0, which is e to the 0, which is 1. And I end up with another issue, 0 over 0. Now this is a difference of perfect squares, so I could have looked at it as e to the x plus 1 times e to the x minus 1 over e to the x minus 1. This is an example, obviously, of the factoring. And I know that even though the limit wasn't calculable up here, by plugging in 0 into this answer down here, I get 1 plus 1, which is 2. So this in its original form would be approaching a y value of 2, but because it came out to be 0 over 0, there would be a hole there instead. So it would be some sort of picture, like this. Okay? And that y value would be 2. Not all indeterminate forms, however, can be evaluated by algebraic manipulation. So you'll see in this example, I can't break this one up. I can't do difference of perfect squares and cancel. It won't work out that way. I don't know how much proof I would need to write down. But if I plugged in 0, I still would get 0 over 0, and it would be a problem. So we've introduced this thing called L'Hopital's rule. It says let f and g be functions that are differentiable on an open interval a, b containing c, except possibly at c itself. So basically, the numerator is going to be assigned f of x. The denominator is going to be assigned g of x. We're going to assume that they're both differentiable functions as is, but maybe they're not differentiable at the point c. Maybe there is a problem at a specific point, the point that we're approaching. Assume that the derivative of the denominator is not 0, because if it is, then we're going to end up with a problem. And what this rule tells us, what L'Hopital's rule tells us, is that this fraction, maybe it's incalculable as is, but its limit will be equal to the limit of their respective derivatives. Okay? Now this says, this result also applies when we have something of the form infinity over infinity, negative infinity over infinity, or infinity over negative infinity, or negative infinity over negative infinity. Basically, when you have an issue and you have an indeterminate fraction, 0 over 0, infinity over infinity, something like that, then L'Hopital's rule will apply. Okay? So here's an example. If I plug in infinity, then my numerator is going to be approaching infinity. And if I plug in infinity down here, I get infinity. Infinity over infinity is not 1. They are different infinities. So my limit is infinity over infinity. If the result is an indeterminate limit, which it is, we're going to use L'Hopital's rule, which says that it should be equivalent. And you're going to see me write LR to show that I actually use L'Hopital's rule. Some people write L, but usually somebody will write something on that equal sign as an indication that you're doing L'Hopital's rule. So this limit should be equivalent to the limit as x approaches infinity of the derivative of the numerator, 1 over x, divided by the derivative of the denominator, 1. Or, this is now equal to just 1 over x, right? If I divide that by 1, then that 1 can disappear. It's irrelevant. Can I evaluate my fraction now? And I absolutely can. If just my denominator is approaching infinity, then this is bottom heavy, which means I am approaching 0 as a final limit. It says continue the process if necessary. So if we ended up with another 0 over 0 or infinity over infinity, then do L'Hopital's rule again. All right, if I plug in 3, I get 2 times 0 and then over 0. That is an indeterminate form, so I can now say that L'Hopital's rule will apply. L'Hopital's rule says the limit as x approaches 3 of 2 times x minus 3 over x squared minus 9 should equal the limit as x approaches 3 of their derivatives. To make this a little easier, I'm going to multiply that 2 through. What's the derivative of 2x minus 6? 2. The derivative of the denominator, 2x. So this is supposed to be equivalent to the limit as x approaches 3 of 1 over x. In other words, 1/3. Again, this only works if we have an indeterminate form to begin with. Otherwise, use a different technique and just plug in as is. You should be able to find the limit right away. Keep going. All right. My numerator is approaching infinity. My denominator is approaching e to the negative infinity. E to the negative infinity would be like 1 over e to the infinity, which would be 0. So what is it? Infinity over 0? Well, is it infinity because the numerator is growing indefinitely? Or is it, you can't calculate it. It theoretically seems like it would be kind of like infinity, but you can't divide by 0, and you certainly can't figure out those two together. So I'm going to apply L'Hopital's rule, which says that this limit should be equivalent to the limit as x approaches infinity of the derivative of the numerator over the derivative of the denominator. Okay. Now, as is, I guess what I should have done right from the beginning is rewrite this as the limit as x approaches infinity of x squared e to the x. But I didn't. So now, I'm going to keep them separate. This numerator is approaching infinity. This denominator is approaching negative 0, which is still 0. And I'm going to apply L'Hopital's rule again. The derivative of the numerator is 2. The derivative of the denominator is going to be negative x. So now I've got 2 being divided by essentially 0. You can't really divide by 0, but if you are dividing by something super close to 0, imagine 2 divided by 0.0000000, 1. Or better yet, imagine 2 pizzas and you're dividing the pizzas into pieces so small that they're incalculable in size. how many pieces would you have? And the answer would be infinity. Now this is a poor example because, like I said, I should have just rewritten it like this in the beginning, and then that would have been calculable. Infinity times infinity is certainly a bigger infinity. But I wanted you to see that you could apply L'Hopital's rule several times and still get the same response. Now, where has this principle come into play and been especially helpful in math in the past? Well, 1 to the infinity might seem as though it should be equal to 1, right? 1 raised to the first power is 1. 1 raised to the 1000th power is still 1. So you would think that 1 raised to the infinity power would be 1, but it's actually not. So we're going to compare that to this particular limit. Let me explain why this is relevant to 1 to the infinity. If infinity is plugged in, if it could be plugged in, to x, then this would be approaching 1 over infinity, which would be 0. So this would be saying the limit of 1 plus 0, which is 1, to the infinity. So what we're doing is we're not just evaluating 1 to the infinity because you can't, it's not a number. We're evaluating the limit as we approach 1, quote unquote, to the infinity. So look at what happens. 1 over infinity, again, is approaching 0. Right? But 1 to the infinity is not. 1 to the infinity is actually approaching e. Here's why. So somebody went through the whole process of doing a proof of this particular theorem. So we've got y being set equal to this function. Then if I take the natural log of both sides, this is what I would get. Well, the natural log of the limit isn't really relevant. I want the natural log of what's inside, so I just reversed those. The rule for exponents in a natural log is that they can drop down out front. Right? We know that. Okay. Now, I wouldn't have thought to do this, but somebody did. X can be rewritten as 1 over x. Why? Oh, I can't tell you other than it makes for an easier problem. Okay? So the numerator now becomes, or the first term now becomes 1 over x. Okay. We then include this as the numerator and 1 over x as the denominator. Okay. Sorry, you should say as x approaches infinity. So we've got the natural log of 1 plus, theoretically, 0. The natural log of 1 would be 0. And this would also be 0. So we've got a 0 over 0 situation, right? Which means we can apply L'Hopital's rule. The derivative of this would be 1 over 1 plus 1 over x times the derivative of what's inside, which is 0 plus, so this right here is x to the negative 1, so negative x to the negative 2. Negative x to the negative 2, right, because they're the same. These can cancel, and I now have 1 over 1 plus 1 over x. If I plug in infinity, then I get 0. Okay. So this becomes the limit as if x approaches infinity, this becomes 1 over 1 plus 0, which is 1. Okay, well I'm going to solve for y by applying e to both sides. These essentially cancel, leaving me y equals e. Well, what was y equal to right from the beginning? it was equal to the limit as x approaches infinity of 1 plus 1 over x to the x. So if in fact this is infinity, then 1 to the infinity is not equal to 1, but rather equal to e, which is why when you take your interest formula, which is what this should resemble to you right from the beginning, looks like interest. When we talk about compounded continuous interest, so infinitely many compounds, that's why your formula goes from a equals p 1 plus or minus r over n to the mt, and converts with more compoundings to pe to the rt. Okay, and there's the theory behind that. That's the end of 8.7.